Hey everybody, my name's Sean and I'm here today to present the ADTA 5340 final project. So in the presentation today, I'm going to go over four different main areas that we were asked to write about for our project. The first is going to be the strategy I developed for a firm. The second are going to be the three big questions we were asked to write about. The third is going to be pre-processing a public data set and then applying that to a machine learning problem. And then the fourth is going to be applying four different machine learning methods in Jupyter Notebook. So the first, let's get into strategy that I decided I'd employ at a firm. The firm that I selected is a company called Purple Air. And Purple Air make air quality sensors. The majority of their use is for individuals who are just wanting to better understand their own air pollution exposure. So a big region or a big reason that people use these is for wildfires, especially in like the western US. You can see in this map here that air quality is really bad during one of these wildfire events, and these are all Purple Air sensors, and they really show that they have a map online that displays all the data. So it really lets you know how the air quality is doing. But one of the main advantages to these sensors is that they're extremely cheap compared with traditional government regulatory monitoring equipment. So these sensors, each one of them costs about $300, whereas a government instrument is going to cost you around $20,000. So you can really enhance the spatial coverage of pollution measurement with these kinds of sensors. As I said, the benefit is for us to allow to understand our own personal exposure to air pollution. So how am I going to actually apply machine learning to this company? So what I'd like to do is use machine learning to build models that can actually correct for sensor measurement errors. So these sensors are not as accurate as the government regulatory instruments, hence the price. But if they're properly calibrated using machine learning techniques, we can improve their performance by quite a bit. And so the reason they're not as accurate is because humidity, temperature, pressure conditions can all influence the measurement of the actual sensors themselves. So I'm going to be talking about building a model to improve that. So yeah, how do we correct these errors? First thing, this is the sensor. This is what it looks like. This is an example of the big regulatory instrument. This is what they look like. But how do we actually correct the errors? First thing you got to do is you got to place sensors next to a regulatory monitor and collect data at the same time. So the data you're collecting, you got to collect not just the sensor pollution, but you also have to collect meteorological data. So again, temperature, humidity, pressure. Got some of those listed here. And what we can do is we can use that information to predict what the regulatory instrument would read at the same time. So we have to apply a machine learning model, and we use these as the feature variables here, and then we use the regulatory pollution as the target variable. And we can, by training our model using these feature variables here, we can actually develop pretty accurate models that allow for these pretty low cost air pollution sensors to predict somewhat reliably and accurately compared with a $20,000 instrument. So it's a really effective technique. And one of the advantages here is that we can, once we have this model developed, we can apply it to all of the different sensors that the company sells. So that just allows for overall high quality measurements at a really low price. And I think the biggest thing that this can add value to the company is it's just going to give a huge competitive advantage over any other sensor manufacturer that is selling similar types of low cost sensors, but again facing trouble with accuracy challenges, which if applying machine learning methods to the sensors, we can overcome those challenges. So part two of what the presentation was about, three big questions. So the first question was to describe the history of AI, and I kind of broke this down into four different main stages through history. The first one started in around 1800, and I have a picture of Maillardet's automaton. And automatons were just these machines that people created that were meant to mimic human behavior and human action. This one here, pretty incredible, but it can actually draw pictures and write poems. I think there's like something like 5 to 7 uh, programs technically stored in this machine here. And if you call on one program, it will draw a certain picture for you or write a certain poem for you. But I see this time in human history as conceptualizing how we can create machines that resemble humans, but they didn't really have a very developed concept of what that would look like. The next time period here is looking at, this is Alan Turing. He wrote a paper, but in this paper, and this was 1950, he wrote a paper and asked the question, instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? And his whole paper was getting at the point of how could we actually teach machines to learn, and I think that quote just really well encapsulates that idea. A few years later at the AI conference, first one kind of, John McCarthy coined the term artificial intelligence for the first time ever. So this time period is kind of the time period which I saw as people conceptualizing how AI would actually work, but not necessarily having the computing power available at that time to put it into action. And then, so the next stage, here in 1996, IBM's Deep Blue beats Garry Kasparov in chess. And I saw that as kind of a defining moment to show that 40 years later, humans have developed artificial intelligence capable of beating the best chess players in the world. And all of this is a result of finally computing power being available to help propel these AI concepts that had been developed decades earlier. And finally, the last stage of the process I saw as the iPhone kind of as a symbol of big data. I think big data is the next thing that's really driving the AI revolution in history. Phones, sensors, really the internet in general, like collecting so much data that the machine learning algorithms that have been developed for decades now have so much more data to be applied to them, and it's just allowing for a new enriched world and a just exponential growth in machine learning in general. And I think just to point out what's kind of driving this revolution or this this change through time is Moore's law, which states that computing power is going to increase exponentially through time. And I just wanted to show us that here. The next question, though, that was asked was to describe 3 sectors of the U.S. economy which utilize machine learning. And first one I want to talk about is the energy and utilities sector. They use forecasting models to forecast meteorological conditions, and especially now when renewable energy is developing, being able to harness the power of the sun and the wind, it's important to be able to predict those phenomenons so that we can actually we can produce enough power for the people we're trying to get it to. And secondly is forecasting the actual energy demand from consumers. So being able to forecast when peaks in energy or surges in energy are needed and then lulls in energy are needed. And a lot of that might be dependent upon holidays and seasons, different times of the year. And then finally, they use machine learning to optimize their grid, troubleshooting any issues along an electric grid. Machine learning can help solve that. And yeah, big increases in spending over the next 5 years expected, from 0.3 billion to 1.1 billion in 2023. Next area I want to talk about is agriculture. Specifically, big data and machine learning in agriculture is called precision agriculture. And what that really means is They're using sensors, GPS, weather forecasting, remote sensing, all these different techniques to optimize agricultural processes. So predicting when a pest outbreak might happen, we can do that now. Optimizing soil nutrition and soil moisture, for example, by utilizing forecasting models and our soil sensors, we can really increase productivity of the crops that we're growing. And then finally, agricultural workers can work with retailers to leverage consumer trends. So when diet trends are happening, agriculture can change the product development and start growing new crops to meet the needs of the changing diet market, essentially. And then again, huge growth expected in the next 4 or 5 years. Last area is the healthcare industry. And one of the big ways healthcare is using analytics is to optimize medical supply chains. It's a big thing right now with coronavirus, but the other area, which I think is a lot more interesting, is being able to use AI to map the human genome. And this is allowing us to do really great things. We can predict diseases now. So if you have your genome mapped, a doctor can tell you which diseases you have or you're more likely to get, or which diseases you might have already. Secondly, they can optimize your diet based upon this information as well. And then I think too, just big data is revolutionizing the way that we interact with people in general. So a lot of healthcare is going online now. So yeah, all three of these industries are really transformed by AI and machine learning. You can see there, healthcare, really significant money being spent in that industry over the next few years, and a ton already. Finally, last question, 3 styles of machine learning. And 3 styles, these are supervised learning, semi-supervised learning, and unsupervised learning. Supervised learning is going to be I think one of the most commonly types of machine learning used, and this is when you have all of your data is labeled. And that means you're taking a set of feature variables and you're using those to predict whatever your labeled data category is. And this is very commonly used in predictive analytics. Kind of the opposite end of the spectrum is unsupervised learning. This is all data is unlabeled, and we're using machine learning algorithms to essentially group or categorize that data based upon different algorithms that have been developed. And the machine learning is doing that all on its own. We're not giving it any areas to consider, any prediction areas to output certain records into. It's doing it all on its own. And then finally, there's an area in between called semi-supervised learning, and this is going to utilize both labeled data and non-labeled data. So we can use labeled data initially to make a prediction model that can predict new records that haven't yet been labeled, and then once we've predicted those new records, we would tag those records as what we could call pseudo-labeled data. And pseudo-labeled data can then be used to train bigger supervised machine learning methods. So it's just all about, really, in this case, maximizing our resources to handle larger data sets that would be too manually intensive for supervised learning. Yes, and so finally, last part of this that I did on my own here, the data pre-processing. And what I did, I accessed a data set from TCEQ, which is the Texas Commission on Environmental Quality. And the data set that I used took temperature, humidity, dew point, and wind speed data all at one location in Denton, Texas. And it's organized by time. So it's got the date column here and the hour column here. And you can see here, they've got question marks for missing values. And it's these data aren't really missing. They've structured the data in a really strange way. So rather than having just these columns here and this data set organized by time like this, they've got this extra row which refers to these columns as well. So you got your dew point here, which means you're not going to get anything in this column, but you will get it here and not here. And they've got that for each column like this. So I had to pre-process this data set to get it looking like this, and I did this in Jupyter Notebook. First thing I did was I had to merge the date and time columns. So you took these two columns here, I merged them together. Second thing I did was to replace these question marks with null values. And then the third thing, I used the group by function in pandas to collapse all of these date and times, collapse all of the columns according to date and time. So we have our final output, which gets rid of this column right here and then organizes it according to date and time into our nice categories that we want. And I have the code here. I'm not going to go through it, but this is what it looked like to do that. And anyways, I'll keep going on. Next step, this is getting into Jupyter now, and we're actually doing some machine learning ourselves. And the first data set that I looked at was the abalone data set. And for the abalone data set, we're predicting the age of these animals. And the way to do it is by counting the number of rings they have. So before going right into the modeling, had to do some pre-processing. So I had to recode the male, female, and infant, the sex column with those variables in it to 0, 1, and 2. And then checked for missing values overall. There weren't, I don't think there were any in this data set. Overall, this data set was pretty clean. Not much needed to be done. I did do exploratory data analysis, and I think the big thing that stood out to me was the height column for these abalones. There were two data points which fell way outside the range of all of the rest. This one here is I think around 0.5, and this one here was 1.1, whereas you can see here all the rest are pretty much less than 0.3. So these were way outside. I actually did run the model with and without these 2 points, and it didn't make a difference. So I decided in the end just to leave them in. So I predicted the age or the number of rings with a linear regression model. But to do that, I had to split the data into training and testing sets. I used 33% of the data for the testing set. Trained the model, got our coefficients, made the model itself, and then applied that model to the test set and evaluated it. And so the R-squared value I got for the linear regression was 0.534. So we can interpret this as the model's explaining about 53% of the variance in the age of the testing data set. Once I had that, I predicted 2 new records. Went through, made up new values for each variable, and then output our data here. And we've got 10 and 8 for the number of rings for each one of these records here. After that, I went and did a 10-fold cross-validation on this data set. And overall, we had a really similar R-squared value, a little bit less. So we can see that this data set may have been slightly more biased towards a higher R-squared value overall. But the negative RMSE was negative 2.23 for the k-fold. And overall, I don't think, again, we can't tell without applying a different model, but this in RMSE is still kind of high. I think when our mean rings for this data set was only 9. So if you have an error of around 2, that's quite a bit of variability compared with the mean itself. But go on, talk about the next one. The next data set here was the adult salary data set. And what we're doing in this one is we have a bunch of different predictor variables, demographic variables on different people, and we're using those data to classify whether someone's income was greater than or less than $50,000. I think this was in like 1997 as well. So first thing I had to do, pre-processing the data, replaced all question marks with null values, and then dropped all the null values. There's a lot in this data set. I think there's 14,000 data points or something in general. I also had to recode the less than 50,000 and greater than 50,000 to 0 and 1. And then finally, I had to recode all of the different feature variables or predictor variables to categorical to run this model itself. This model had a lot of categorical variables. So rather than printing out all of the histograms and scatter plots on this slide, printed out a few bar plots because they're easier for histogram or for categorical variables. You can see that most of the data set, the income, was less than 50,000. You can see that also just in general there were more men in the data set than women, and education overall for people, most of the data set had at least a high school were high school graduates, whereas also had a lot that had some college education, and then the next highest was bachelor's degree. Ran a logistic regression on this model or on this data, and again split the data into testing and training, trained the model and applied our model to test and evaluate. And so here is the accuracy metrics that I got here. The model had an 80% accuracy overall, also an 80% k-fold accuracy, so pretty consistent between the two. And I think the things that stood out for me though were not the accuracy itself, but I looked at the recall, and what this tells us is that our 0 here, so this is the less than 50,000, our model predicted 95% of all people that made less than 50,000 correctly in the data set. But our model only predicted 36% of all people that made over 50,000 correctly. So even though the accuracy is 80%, it seems like our model is not that great at predicting those that do have income higher than $50,000. So it's something to consider for improving this model, I think. So I did predict 3 new values with this one. I made all of these characteristics the same except for capital gains and sex. I was trying to see what could shift whether someone made over 50 or less than 50,000. And with all of these characteristics here, the income for a male with capital gains of 3,000 was over 50,000. With the exact same characteristics, the model predicted that a female would not make over 50,000. Thought that was interesting. So I started messing with the capital gains to see what it would take to get the model to predict whether a female would make, when a female would make 50,000 or over, and that was when a female had 5,000 in capital gains. That was like the threshold there. The next thing that I looked at was the clustering model that we made. So we had a data set full of cars, and it had different attributes about the cars themselves. And we were to cluster these cars according to their attributes into 4 different groups using the k-means clustering algorithm. So this is an unsupervised data set, which means we're not actually using the labeled data to predict any value or anything. What I had to do first, I had to pre-process the data. So 2 columns had more for a variable in there. The one had 5 or more, another just had more. For one of those, I had to strip more from the column itself to leave 5 only. And the other one, which only had more, I had to replace more with 5 in order to get those to be in just numerical format. Checked for missing values, and then also recoded all the variables into a categorical numerical format so that the model could be prepared. The different variables we had in this one were price, maintenance, doors, passengers, luggage, and safety. And this you couldn't really do exploratory data analysis, at least in terms of the histograms and the scatter plots, because they're all categorical. But I did make some bar plots to just have a look and see what the different distributions of these were. And all of these categorical variables had the same distributions overall, so I didn't put them up here, but they all had roughly equal distributions. And then the evaluation column, which is one that we're not actually using in this algorithm, but it is what we can compare our results to. It had mostly unacceptable conditions for these cars, and then acceptable was the next highest. So I just wanted to point that out. Finally, the algorithm I used, as said before, k-means clustering. We had 4 cluster groups that we were creating, and again, to kind of compare those groups to this evaluation column that we have here. Euclidean distance was used to sort the cars into different groups, but that's the default in scikit-learn for k-means. And then finally, once we ran the algorithm, we could identify whether the clusters that were created were similar to these conditions over here. So did it actually sort it into those categories, or was it something different? So once you run the algorithm, you get centroids for each cluster group. Again, we have four groups that we made. So these are the different centroids right here, and this is a 6-dimensional centroid. And what was interesting, though, is that it seemed like the algorithm did not separate the data according to passengers, luggage, and safety overall. These averaged out to all be 1. But the algorithm did mostly discriminate data according to price, maintenance, and doors. So you can see that this row right here, 2.5 for the price, that's going to be this one right here. This one right here, 1.6 and 1.5, that's going to be these two right here. And then finally, our 0.4 is going to be this one right here. So at least according to price and maintenance, I'm plotting them. You can see how these 4 groups kind of sorted themselves out. This is only a 2-dimensional representation. We wouldn't have this overlap if we could actually plot this out in 6 dimensions, but can't do that, so we're stuck with this visualization. I did create new records and predicted those records according to the algorithm itself. And the first one was just a random record I made up, and we got group 3. So this one right here, or sorry, no, this one right here. This is 0, 1, 2, and 3. But the second one, I actually, for record 2, I wanted to make a record that would be similar to this row right here. So just to see, making sure things were working correctly, and I did end up getting 0 for that. And then for the third record, I wanted to do one that would be similar to this centroid mean right here. So, and I did get one similar to that. So that shows me the algorithm and the model we built is working fine. Finally, the last thing I did was compare the classification groups to the actual the evaluation column that we had, and I found that it doesn't seem like the algorithm classified the data set into the same categories as our evaluation column, because mainly this unacceptable category had 1,210 data points in it, whereas there's no actual category that we created in the clustering algorithm that has nearly that many data points. So I think our classification algorithm or clustering algorithm was mainly focused on these 3 variables and wasn't necessarily representing the condition the way that this column was in the data set. So last thing that we had in this data set was to evaluate different models. And the first thing we did was I used this abalone data set again, and I used a regression tree and the linear regression that we did already. So the regression tree, the results are right here. It did a lot worse than the linear regression. significantly worse. The R-squared value was 0.13, whereas linear regression was 0.534. So like a 4-time difference there. So it tells us that the linear regression is going to be a lot better at predicting the age of the abalones overall. K-fold values were both similar to the test evaluation. And while the NMRSE, it seems like it looks a little closer. If you really look at it, it's quite a bit different still. There's a 27% difference between the two, and again, that mean value was only 9.9. So an error of -3 or -2.23 makes a big difference when your mean age value is only 9. If our mean was 40 or 50, that error wouldn't be as bad, but in this case it is. And finally, I predicted the same records as before using the regression tree as well, and we got 13 for this one here, so it over predicted by quite a bit, and 9 for this one. And if we're going to trust which model actually predicted more accurately, because of these metrics over here, we'd assume that the linear regression did better. Finally, the last one that I looked at was the adult salary, classifying that income again. And so we had our logistic regression. Here are the results here that we got earlier. I also used the k nearest neighbors model, and I used a k of 5 to build the model itself. And for this model, we had a lot higher accuracy, 84% compared with 80%. But I don't even think, to me, that was the most impressive thing. I think the best thing about this model is that our recall here is 90%, which this isn't as good as the logistic regression, but for the people who made over $50,000, our recall was 64%. So this model predicted 64% of all of the people in the data set who made over 50,000 correctly, whereas this one only predicted 36% of those people. So this KNN model here, far superior with respect to predicting over 50,000 at least. Under 50,000, not as great, but overall still pretty good. So if I were to choose one of these models, I'd select the KNN. Also pretty interesting, I used those same 3 records to predict 3 new records with the KNN, and they all turned out to be under 50,000. So if we're going to choose one model here, again, we'd have to choose this KNN as likely the more accurate one, because of the metrics that we've got here overall. But that's all I've got today. I think I'm about to run out of time. So thank you for listening, and good luck for everyone else. Have a happy Christmas and